Hello students, my name is Mamta, Assistant Professor in Mechanical Engineering Department. Today I am discussing thermodynamics. So thermodynamics is basically, just a moment, just starting. Okay, thermodynamics is basically a branch of science that deals with energy and the related properties of matter, especially the law of transformation of heat into other forms of energy, and other forms of energy can be transformed into heat also. So we have basically two kind of approaches in the thermodynamics: macroscopic approach and microscopic approach. Thermodynamics is basically combination of thermo and dynamics. Thermo means temperature, and dynamics is basically the branch of physics, and it deals with the motion and forces that affect the motion of objects. Basically it involves the various concepts such as velocity, acceleration, momentum, where and the force is also acting upon the object, right? So thermodynamics is combination of movement with applying of forces and temperature. Okay, so these are the two approaches which I am discussing here, that is macroscopic approach and microscopic approach. Okay, so macroscopic approach is, it deals with the study of thermodynamic system as a whole, and it focuses on overall properties that such as temperature, pressure, volume, energy. Okay, so it actually does not consider individual particles like molecules. It doesn't consider here, and instead of that it examines the system's behavior and properties on large scale, right? So this approach is basically useful for understanding and predicting the bulk behavior of system, and applied in engineering and practical applications. So if we talk about the microscopic approach, this is the approach where we are we find out the interaction of molecules within the thermodynamic system. Okay, it focuses on the statistical behavior of particles and statistical mechanics to describe the system properties and energy distribution at molecular level. Okay, so here we consider the movement and interaction and energies of individual particles to understand and explain the macroscopic behavior of the system. Okay, so microscopic approach is particularly studying the behavior of gases, liquid, and solids here. Okay, now uh, it is the thermodynamic system. This is the in this picture. This is the system, and this imaginary line is boundary, and other than that, this is the surrounding. So thermodynamic system, it is defined by using real or imaginary boundary. Anything beyond real or imaginary boundary is known as surrounding. Okay, so to define a thermodynamic system, we typically draw a boundary around it. We separate it from the surrounding environment. Okay, so this boundary, it can be real or imaginary, right? So this can be real or imaginary, and the surrounding, it refers to everything that exists outside the defined system. Okay, so it basically encompasses the external environment or rest of the universe that interact with the system. Right, so surrounding can exchange energy such as heat and work, we can say, within the system through the boundary. So by defining a system and its surrounding, we can analyze the interaction and energy exchange between them. Okay. So now this is these are the definitions of thermodynamic terminologies, that the thermodynamic system, this is the system, it defined as the quantity of matter or definite region in space upon which some thermodynamic processes is taking place, right? It is basically a region of space or specific set of matter, right? So this system can be real or the meaning which physically exists, okay, or it can be imaginary, which is used to construct for the theoretical purposes. Okay, right. So now these are surroundings, boundary, universe. So surrounding is the space outside the thermodynamic system. This is the space outside the thermodynamic system, and the boundary is partition between system and the surrounding, right? So bounding, a boundary is the line separating the system and surrounding is no and system and surrounding is known as boundary, right? So next we have universe. Universe is combination of system, surrounding, and boundary. Okay, so this is the universe. And if we talk about the state of the system, state is basically the macroscopic condition of thermodynamic system. So if we talk about the thermodynamic parameters such as pressure, temperature, density. So these parameters basically define a state of the system. For example, if this is a flask, if there is some of the liquid at some pressure, some temperature. Okay, so for example, it is at 1 bar, it is 20 degrees Celsius. So this is the basic particular state of that system. It is at some of the pressure, it has a some temperature, it has some of volume. Okay, so it defines as the state of the system, right? So now we are classifying the basic thermodynamic systems, and it is open system, closed system, and isolated system. So an open system is a thermodynamic system that exchange both energy and matter with its surroundings, right? So here the mass is exchanged and energy is also exchanged. Okay, here both heat and mass can flow across the system boundary. Open systems are often found in nature in many engineering applications. For example, if we include a pot of boiling water on a stove, so here heat is transferred to the water and water vapors released into the surrounding. Okay, and another example we can take of us is a living organism that takes in nutrients and expels waste products, right? So next we have is closed system. So this is the closed system. So in closed system, mass cannot be transferred and energy can be transferred. Okay, so this is the thermodynamic system that can exchange energy with its surrounding, but not matter. But mass cannot be transferred. Okay, so the system boundaries, it's imperable to mass transfer, but it allows for the transfer of heat and work. Okay, so total energy within a closed system, it remains constant. Okay, so but the distribution of energy among the different forms, it may exchange, right? So common example of this closed system is a sealed container filled with the gas, where gas can be compressed or expanded, but heat can be transferred into or out of the system, right? But mass is constant here. Okay. Next we have is isolated system. In the isolated system, we the mass is cannot be exchanged. Also, energy cannot be transferred. So, in this kind of thermodynamic system, the exchange of energy or matter within with its surrounding cannot be transferred. Okay, so it is completely sealed off from the any external influence, or we can say it is insulated system also can be said. So in isolated system, the total energy, including internal energy, it remains constant. That means no heat or work is transferred across the system. So isolated system, these are basically constructs to use for the practical analysis only. Okay, so basically truly isolated system, it doesn't exist in practice. Okay, some of the energy can transferred. Okay, so it doesn't exist in practical way. Okay, so example is some well insulated system, we can say thermoflask. It closely, this is can be approximate example we can say, but it's not a perfect example. Okay, so it can be used for the practical purposes, right? So these were the systems we can we classify for the thermodynamics. Okay, now coming to the thermodynamic equilibrium. So these are the three kind of equilibrium we are discussing here: chemical equilibrium, mechanical, and thermal equilibrium. So basically equilibrium is the indicate the state of balance. When there is no unbalanced potential within the system, it is called as a equilibrium condition, right? So in chemical equilibrium, there is no chemical reaction or diffusion of matter from one part of the system to another. So it is called as chemical equilibrium. It basically chemical equilibrium is a balanced condition Okay. Now, next is mechanical equilibrium. In mechanical equilibrium, there will be no unbalanced forces in the system. The system is said to be a mechanical equilibrium. Okay, for example, we do shear force and bending moment questions where we balance all the forces upward and downward, right? Similarly, in thermal equilibrium is a state where two or more systems these are at the same temperature, where no net transfer of heat is between them. Okay, when the two systems have different temperature, one is hotter and another is colder, when they come in contact with each other, then the at some of the point, they both of them will be of same temperature. Okay, and there will be no heat transfer between each other. Okay, then it will be called as mechanical equilibrium, sorry, thermal equilibrium condition, right? Then we have thermodynamic properties of a system, right? So these are the properties which characterize the system for the defining a system, okay, such as volume, pressure, temperature, viscosity, etc. So we are classifying the properties of a thermodynamic system in two ways: intensive properties and extensive properties. Okay, so intensive properties are the properties which are independent of temperature, sorry, independent of mass, right? So in is basically independent, shows independent, right? So in the intensive properties are those properties which have same value of for any part of the system, okay, and those properties which are independent of mass of the system. For example, temperature, pressure, and density. Okay, right. Then we have extensive property. Extensive properties are the properties which depends on the mass, and it do not maintain the same value for any part of the system. Examples are mass, enthalpy, volume, and energy, etc. Okay, so now we are just coming to the path, process, and cycles. So if uh, we have already mentioned that the state is basically one position of any of the system. Okay, for example, some of the pressure we have, temperature we have, volume we have. Okay, and path is the change of state. For example, this is pressure and this is volume. There is P1, this is basically defined one state, okay, and this is basically defined second state. When it is coming to one state to second state, then it is called as a path. Okay, so if all the changes of state of the system are plotted, then line joining the change of state. This is the change of state P1 to P2. Okay, so yeah, this is 1 to 2. This is the change of state, right? So it is called as path. And if we talk about the process, it is the complete description of change of state of a thermodynamic system through a specified path. For example, this is one path, and if it is following another path, it is called as process, right? This is one process. Then we have cycle is basically defined as the series of change of state, okay, such as initial state is identical with the final state. If state one is initial state is equal to final state, this will called as cyclic process. Okay, we will discuss further. Now, this is a quasi-static process in the system. We are This is basically we have considered a system where the gas is contained in the cylinder. We can see in the figure. Okay, so it is an equilibrium state. It represents the properties of pressure, volume, and temperature, and the weight on the piston. It balances the force exerted by the gas. Okay, so when it is P1, P2, and T1, it is just one state of the system. Okay, when the weight is removed from the piston, the system becomes unbalanced. Okay, so unbalanced forces between the system and the surrounding, and the gas pressure will move the piston in upward direction. Okay, so system comes to the again comes to the equilibrium state, but the state will be changed to P2, V2, and T2. Okay, so The figure here shows that the point 1 and 2 as the initial and final equilibrium state. This is the state 1, this is the state 2, and these are the two equilibrium states. Right. So, if the single weight on the piston is made up of many very small pieces of weights, so if these weights are removed one by one, very slowly at any instant of upward travel of piston, and if the gas is isolated, means when there is no mass transfer and energy transfer, the departure of state of the system from the thermodynamic equilibrium state will be infinitesimally small. Okay, so every state passed through by the system will be an equilibrium state. Okay, so these are the different equilibrium state and quasi-static processes, right? Now, these are the forms of energy, work, and heat. So, work is one of the basic mode of energy transfer when the action of force on a moving body is identified. Okay, so work done by the a force, it acts upon a body in moving in direction of force. But basically, work is force into distance. Okay, force is applied to a body when it travels to some of the distance. Okay, in thermodynamics, work transfer is considered as occurring between system and surrounding. So work is said to be done by a system if sole effect on the things external to the system, it can reduce to raising of the weight. Okay, so work is done by the system. If the work is done by the system, it is taken to be positive, and if the work is the on a system, then it is taken to be negative. Okay, so now we have power. The rate of energy transfer is known as power, or rate of work transfer is known as, okay, power. So units is joules per second or watt, right? Then we have heat is defined as the form of energy which is transferred across the boundary by virtue of temperature difference, right? So temperature difference is basically potential of force and heat transfer. Okay. Then we have heat flows into when heat flows into a system is taken to be positive, and when heat flows out of a system, it is taken to be negative. Okay. Now, this is the process in which no transfer of heat through the boundary is known as the adiabatic process. Okay, so this is the picture of work done by the system where the internal energy of when the work is done by the system, the system's internal energy decreases, and when work is done on the system's internal energy increases. Okay, so now we have types of heat. Specific heat, we can say specific heat is defined as the amount of heat it is required to raise the temperature of unit mass is 1 kg, and with the substance of by unit degree 1 degree Celsius, right, or 1 Kelvin, we can say. Okay, so the formula is here mcdt. Mcdt is basically change in temperature rise or drop in degree Celsius or Kelvin. Okay, mass, M is mass, and C is your specific heat in kilojoules per kilogram Kelvin, right? So we have types of specific heat at constant pressure and constant volume. When it is said to be constant volume, then if at that time volume will be constant throughout the reaction or system. Okay, so amount of heat that is required to raise the temperature of unit mass of the substance by unit degree, that is 1 degree Celsius, 1 Kelvin, and the change in temperature when the volume is constant, right? Specific heat of water we have given here, it is standard values. Okay, units are kilojoules per kilogram Kelvin, and the latent heat of vaporization, we can say. Okay, at a constant pressure, the pressure will be constant, right? For the specific heat. Now latent heat of vaporization, it is defined as the amount of heat required to evaporate in 1 kilogram of water at its saturation temperature. Okay, saturation temperature is basically a boiling point. Okay, so it is represented by HFG, which is like that. Okay, so unit is kilojoules per kilogram, and this is the value of latent heat of vaporization of water. Okay, or we can say latent heat of steam. Now coming to the different processes of thermodynamic system. Okay, so first is isobaric. Isobaric process is a thermodynamic process in which pressure of the system remains constant. Okay, and it means that the system is allowed to exchange energy and perform work while maintaining a constant pressure. Okay, so volume and temperature of system can change during the isobaric process. Okay, so here the pressure will be constant. Okay, constant, and others volume, and they can be changed during the isobaric process. Now we have isochoric process. Basically, iso means same, and bar is the unit of pressure, right? So from that we can take an idea. Okay, then we have isochoric process. Isochoric process also known as isovolumetric or constant volume process. Okay, so it is a process in which volume of a system remains constant. Okay, and no work is done by or on the system against external pressure. Okay, so system basically does not change its volume. Heat transfer can occur resulting in changes in temperature and pressure, right? So next we have a isothermal. So here the thermal means temperature, right? In isothermal process, temperature is taken constant. Okay, the system exchange heat within its surrounding to maintain a constant temperature. Okay, so pressure and volume of the system can change during the isothermal process, right? Next we have is adiabatic process. Okay, so in adiabatic process, there is no heat exchange between the system and its surrounding. Okay, so no heat transfer occurs into or out of the system during an adiabatic process. It means that the change in the system's internal energy uh, will be will not be changed, right? Okay, it only depends on the work done on or by the system. Okay, so temperature, pressure, and volume of the system can change during the adiabatic process. Okay, there will be only heat will be not be transferred, right? Next, we have a cyclic process. Cyclic process is a thermodynamics process in which system undergoes a series of state of changes. Okay, it changes in one state, two state, then three, then four, then it comes to original position one. So then it will be called as a cyclic process. Okay, the initial state of the system, it should be identical to the final state. Okay, so it is basically results in a closed loop. This is a kind of closed loop. For example, pressure and volume, when it covers a one path to second path, then comes to original position, it is called as cyclic process, right? Okay, so this cyclic process, it is utilizing various energy conversion systems, and that can be analyzed to assess the efficiency and performance of such systems, right? So by understanding these processes, we can apply in various we can find out the various thermodynamic properties, and we can predict the behavior of the system, right? So that's it from my side. Thank you so much for your patience and listening. Thank you.